Interval analysis for proving the stability properties of robots. In this talk, I will present interval analysis, and I will show how it can be used for proving stability of nonlinear system, nonlinear dynamic system. As an application, I will consider sailboat robots, and more precisely the robot vaimos, which is a collaboration between Ensta Bretagne, and Ifremer. So this work has involved several people from Ensta, such as Fabrice Lebars, myself, and Olivier Ménage and Patrick Rousseau from Ifremer. What is interval analysis? Interval analysis is a tool, numerical tool, which is adapted to prove that a function f from Rn, so x belongs to Rn, to R, for instance, and I want to prove that this function is always positive over a box. So I consider, for instance, a box. In this case, it will be an interval, but in the general case, it will be something like this if I am in R2, or something more complicated if I have in Rn. Of course, it's a Cartesian product of intervals. So if I have a box such as this one, the image of a box will be here this, and the minimum, and this. So the image of a box will be something, the image of this interval will be this interval. So this interval or boxes will be denoted by brackets like this, x, and this one is the image of the box x. For higher dimension, box will have such, will correspond to box instead of intervals as here. So interval analysis is a tool that makes me possible to prove that f of x, the image of a box, is always positive. So always positive, it's better to write included. So it's a subset of R plus. If you prefer, I can write it like this. I want to show that for all x belongs to x, to the box x, which is included in Rn, I want to prove that f of x is positive. So interval analysis is a right tool to prove such properties in the case where f is nonlinear, non-convex, and so on. So f is a combination of sine plus elementary operator, such as this one, division, multiplication, exponential, absolute value, and so on. I will show how it works. Now, consider, for instance, this function. This function combines multiplication as two inputs, x1 and x2, and combines multiplication. So the minus, the cosine, sine, multiplication again, and so on. And I want to know or to prove that my question is this always positive for x1, x2 belongs to minus 1, 1. So this corresponds to a box in the x1, x2 space. How can I do this? For this, I have to introduce interval arithmetic. So what is interval arithmetic? For interval arithmetic, I will consider two intervals, for instance, -1 and 3, and I will add this interval with another interval, 2, 5, for instance. And I want to know the result of this. So the semantic we have is we have to think about a random variable a, which belongs to -1, 3. Another variable b, which belongs to 2, 5. Then what can I say about a plus b? To which interval it belongs? So of course it is quite natural to say that it will be in this case +1 and 8. Why? Because -1 plus 2 is 1, 3 plus 5 is 8. So I have added the lower bound and the upper bound. What about the multiplication? I take the same interval, -1, 3, multiply by 2, 5. What does that mean? So if A belongs to this and B belongs to this, what can I say about the multiplication? So we can say that, in fact, I can reach, for instance, A equal to, say, -1 and B is equal to 2, I will obtain -2. Okay. If A is -1 and B equal to 5, I will obtain -5. 3 multiplied by 2 is 6. 3 multiplied by 5 is 15. So I can obtain these 4 numbers depending of the value of A and B. Now I will take the smallest interval which encloses this set, and I will obtain the interval -5, 15. So I can define the multiplication of two intervals by taking all extreme points, all lower and upper bound. I multiply all of them, I take the smallest interval, and I obtain the resulting interval. So if you want, A multiplied by B belongs to this interval. Okay, so I have defined here the addition, I have defined the multiplication, but I can also define some other operation, such as sine, cos, and so on. Let me consider, for instance, the absolute value. So the absolute value of the interval -7, 1, for instance, what does this mean? It means that if A belongs to this, what about the absolute value of A belongs to which interval? So I will take, of course, if A equal to -7, I will obtain 7. If A equal to 1, I will obtain 1. But A can also be equal to 0, so of course I will obtain 0 and 7. So here we have an idea of what means interval arithmetic, and I will show now why we will use interval arithmetic for proving that the function is always positive. So I consider here the interval extension of this function, the initial function, and I will replace this function by the same function, but using interval instead of real numbers. I obtain an interval expression for which I am able to use interval arithmetic. If the result is, so there is a Moore theorem, that will be explained now, which tells you that if the resulting image I obtain using interval arithmetic is positive, so if it is included in R plus, then I have a proof that for all x belonging to the initial interval, so in our example it was minus 1, 1, then the function will be positive. It is important. It means that interval arithmetic is a nice tool, an efficient tool to prove for large class of functions that the image of a box is always positive. Okay, now I will try to use interval arithmetic in the context of sailboat robotics in order to prove properties of dynamical system. So in Brest, we have started since maybe almost 10 years sailboat robots. First was Brest Spirit, which was the goal of Brest Spirit was to cross the Atlantic Ocean. It has first been started by crossing the Rade de Brest. So of course it has to go from Brest, the center of Brest, to l'École Navale. But it failed here, but it was a good success since it has crossed the Rade de Brest. So it was very motivating for students. So this boat has been built by students. And of course, because of a lot of mechanical problems, the robots always failed to cross the Atlantic Ocean. Other people, such as École Navale, wanted to also to cross the ocean. So you can see here the Erwan boat of École Navale, which was very efficient, but it also failed after several hundred kilometers. And here we have the robot vaimos, which is a result from the yellow one, not the small one. The small one is a small robot built also by students with a low-cost robot, but vaimos is a yellow boat, which is a collaboration between ENSTA and Ifremer. Here we see the vaimos moving inside the lake of Angers. Angers is a town in the center of France. At the top of the mast, here you have the wind sensor, which is able to measure the speed of the wind, but also its direction. You have here a balance ring. You can tune using the main sheet here. You can tune the angle of the sail. And you have also at the back a rudder, which makes it possible to influence the direction of the boat. Another sensor inside the boat, you have a small inertial central and a compass, which allow the robot to measure the direction of its direction. You have a GPS also, which measures the position, but also the speed of the robot. So this is a presentation of vaimos. It is totally autonomous in this video. A sailboat can be described by a nonlinear differential equation. A possible model is represented here. The state variables are x and y, the position of the robot, theta, the heading, the speed, the rotation speed, the force on the sail, the force on the rudder, Here, a condition which tells you that when it is negative, it means that the sail behaves like a flag. Otherwise, the angle of the sail corresponds to the length of the main sheet. So U2 corresponds to the length of the main sheet, and U1, the other input, corresponds to the angle of the rudder. So I will show on a simple picture how it works. I have here my boat. I will represent here the sail, here the rudder, here I will represent the wind, and the rudder, and on the rudder I will the wind will make on the sail a force. A force like this. And the water will make on the rudder another force, like this, for instance. And this corresponds to the force on the sail, the force on the rudder. The two inputs are the angle of the rudder, so it corresponds to U1, and the other input is the length of the main sheet. So the main sheet is a rope which links the sail to the center of the boat. So here it will correspond to U2. So the wind makes a force Fs, and due to the keel, so the keel is below the robot, I represent like this, the robot will go to this direction. So, for example, this direction. And it will correspond to a speed vector, and the speed will be denoted by V. So here I have almost all my variable. I will draw here will represent x1 and x2. The center of the boat, x and y, excuse me, it's x and y. So I have drawn all the variables that are involved, almost all of the variables that are involved in my model. So my sailboat corresponds to a system, x dot equal to f of x and u. The input u corresponds to the angle of the rudder and the length of the main sheet. And I will assume that I measure x. So since I have an expression for f, I will be able to simulate it. So here is my sailboat. I will try to simulate it. I have the wind, which is represented by the arrow, and I will start the simulation. So it moves like this. I stop. You can see here that I can move the sail with the keyboard, okay, and I can move also the rudder. So I will try to simulate it like this. For instance, I turn, I will change the rudder to go like this, So I tune the rudder, I open the sail. I will try to turn like this. Oops. So I am able to control my boat by hand. But it is not yet a robot, it is a sailboat. If I want to transform the sailboat into a robot, I have to add a controller. So I add here a controller. The controller will be linked here, like this, and it will generate the input U, like this. And here I will have the same point, what I want. Here it is the controller. What we have here, it is a closed loop system, and it corresponds to what we call a robot. Here we have the sailboat, but the sailboat plus the controller corresponds to a robot. So the controller has the form U equal G of X, and then the robot will be autonomous, so it has not any more input or only the set points. So it will have the form X dot equal F of X. Now, due to some uncertainty, I will not have exactly X dot equal of F of X, but it's only an approximation, so I will have a set of feasible F of X, and when I have uncertainty, I will represent by this equation by a differential inclusion. X dot belongs to F of X. So let me explain maybe on a picture. Classically, if I know X, if I know the state, I am able to have a direction where the state will move. Okay. So in a near future, here I will have X of t plus dt, which will go in the direction of f, whereas here I have x of t. So if you prefer, I can say that I have x of t plus dt, where dt is small, is equal to x of t plus dt multiplied by f of x of t. So it is a Euler method, and if I apply it several times, I will obtain a trajectory, the trajectory for my robot. So it is the case if I have x dot equal to f of x. Now, what happened in practice is that I do not have a single f of x, but different possible f of x. So if I take all of them, I will obtain something like this, and I will obtain a set of possible f of x. So when I have uncertainty, I will call it f of x. and I will not have anymore x dot exactly equal to f of x, but x dot belongs to f of x. So I'm not totally deterministic. So it is more difficult to integrate. It's not anymore possible to integrate a trajectory, but it corresponds to the reality where I have some uncertainties. I will now propose a controller aligned to so that the boat will follow a line. Here I have my robot. The inputs will be the angle of the rudder and the maximum angle of the sail, which corresponds to the length of the main sheet, which has the role of a stop for the sail. And what I am able to measure is the position of the robot, the heading of the robot, but also the direction of the wind. With this, I will, as input to a controller, what I want to follow. I want my robot to follow a line, AB. That's what I want. So I want to build this controller. So the controller will be decomposed into two controllers. The first is the inner loop, or the heading controller, which control directly the inputs, the angle of the rudder and the length of the main sheet, with respect to a desired direction, theta bar. So it is the direction where I want to go. And this direction is computed using a vector field method. So that's what I will try to explain now. So the heading controller will have this form. I will first explain how to tune the rudder. So I will try to explain this formula on a picture. I consider here my robot. So my robot is represented like this by a triangle. And this robot has a direction. This robot has a direction, say, theta. The robot has a rudder here, and it wants to go to the direction theta bar. Normally, a classical controller would be not this one, but would be to say that the angle for the rudder that I can tune, which corresponds to U1, should be something like a coefficient K times theta bar minus theta. So it is a classical proportional controller. So what happened with this formula? If this one is almost equal to 0 and this one is almost equal to 2p, then the controller will consider that here theta bar minus theta is almost equal to 2p, and the rudder will not be straight, whereas I do not see any error. So it is a modulo 2p problem. To avoid this, I will consider the specific function that I will try to draw now. Which is a sawteeth function. So I will represent like this. And this function will have this shape. So I will better consider so this shape. So around 0, it is the identity. And it will be periodic like this. And so on. And due to this periodicity, so here I will have something like a pi minus pi. So of course, and here I will represent theta bar minus theta. So this function, if I call it, for instance, theta tilde, the green function I am now representing will have this equation. So let's call it, for instance, phi of theta tilde. Phi of theta tilde is equal to theta bar minus theta divided by 2. And then, as here, it will be tangent of this arctangent of this. And here, I will have to multiply by 2 divided by p. So this function corresponds to the green function represented here. So this makes it possible to avoid the modulo 2p problem. I mean, if I take one of this angle, and if I add 2 pi, then the error will not change. Okay, so this is why, to avoid this modulo 2p problem, I will filter my error by this function. Now, this function will be equal to 1 when I will have a maximum equal to 1. That's why here I will multiply by the angle, the maximum angle for the rudder I want. It was an explanation for the rudder. So if I have here, it corresponds to the direction of theta bar. If I'm going to this direction, then the rudder will not be influenced. If I am far from this direction, then the rudder will be at its maximum. What about the tuning of the sail? The tuning of the sail is given by this equation, which corresponds to the cardioid model. So what is a cardioid model? It corresponds to the cardioid function, which is represented here in polar form. Maybe I will try to show on a picture again. I have here the direction of the wind, let's say psi. And my boat, assume that my boat is like this. So now I don't care anymore about the rudder, but just of the sail. So in this case, the sail should be open. at the maximum, so that the force will be like this also at the maximum. So it will correspond to an angle maximum of delta sail maximum, or to U2 will be equal to P divided by 2. Another situation is if my robot is like this, then the sail should be more closed. Okay, and if I am against the wind, like this, then the sail should be totally closed. So it means in this situation that delta sail max equal to 0. So what I have represented here in this picture, this intuition, corresponds to the cardioid model. So when psi equal to theta, this will be equal to 1, so it means that I want to go with the wind. So the cos of 0 will be equal to 1, so I will have 2 divided by 2, and the angle will be equal to P divided by 2, as represented here. So this corresponds to 0 for psi minus theta bar, and my sail is open, totally open. This point here, or this one, corresponds to this situation, and the last situation, this one, where the angle is equal to 0, corresponds to this point. So I have a simple formula which tells me how to tune the sail. So I have explained now my low-level controller, or the heading controller, or also the inner loop, which is given here. Now this controller, as explained before, I have to feed it with the direction where I want to go. So in order to do this, I will have to introduce the vector field I will use. So I have my robot, and I want my robot to follow a line, and I will describe the behavior of the robot with respect to the line by a vector field. So if I am here, I will follow this direction. If I am here, I will follow another direction. So this line will be attractive. The equation of this vector field is given by this formula. So phi is the angle of the line, E is the distance between my point to the line, and R is the accuracy. So if I want, for instance, to be at a distance of 10 meters to my line, so it is an approximation, for instance, of the GPS, then R will be equal to 10 meters. So if I apply this equation, I will obtain this kind of vector field. It is what we call the nominal vector field. Now, what happens is that if there is some direction I can follow, if I try to follow this vector field, it could be with a motorboat, it could be perfect, but I have a sailboat, and there is some direction that I have to avoid. And this direction corresponds to an inequality which involves the angle of the wind, the angle of my boat, the heading of my boat, and also an angle which tells me that I am not able with my boat to go against the wind with an angle lower than delta. So if I satisfy this inequality, it means that theta is not feasible. On this software, the black arrows corresponds to the vector field, to the nominal vector field. Here, this line corresponds to the line AB I want to follow. So this line makes the vector field attractive. So this line is attractive. This arrow corresponds to the wind. If I move the wind, some arrows becomes unfeasible. So unfeasible means that the red arrows corresponds to direction which are in the magenta cone. So this is the wind and it is the no-go zone. I'm not allowed to go with respect to direction that are inside the magenta cone. That's why the arrows are red. So if the wind is like this, everything is okay. It's like this, some arrows are not okay. And like this, all arrows are unfeasible. In blue, we can see the size of the corridor where I want to be. So this corresponds to R. When I move R, we can see that the corridor changed, and what I want for a sailboat is to be something like 20 meters to the line. Most of the time in the ocean, it's sufficient. It depends of how accurate I want to be. Okay, so what to do when I have some arrows like this? The idea is to take an arrow and to project it in order to have a direction which is feasible, what I call the polar projection. So if I project it, it means that, for instance, the red arrows like this are projected either to this side or to this side. I will choose the side, so the magenta direction, which corresponds to a direction which makes me go toward the line AB. So for instance, that's why I will project this arrow toward this direction and not toward to this direction. Okay, so now I have this, and when I move, we can see that I will have always feasible direction. And what is important to see is that the arrow makes me possible to go from outside to inside my corridor. So if I am outside the corridor, I will be attracted by the corridor. And here I can maneuver. Okay, it will be important to have a zone where I can maneuver. If I want, because when I build my regulator, I don't know the wind. So I will try to draw my differential inclusion in order to explain, in order to model the fact that I don't know where the wind comes from. So I will take all wind. And if I take all wind, I will obtain the differential inclusion. As we can see, there is a corridor where I need to maneuver. When I am outside this small corridor, I want to go towards the line. So I can draw some simulation with different points. So I will consider a wind. Let me consider a wind like this. And I will take different initial condition and draw some simulation. Okay. So with different initial condition, I follow it corresponds to the behavior of my boat. But when the wind is like this, I will draw again some other simulation, and I will go against the wind. So we can see that here I maneuver, and I have to tack in order to be able to go against the wind. So we can see with simulation that everything seems to be, if I am here I follow the nominal field, but when I am here, it's different. Okay. Okay. So what is important to understand is when the direction, nominal direction, is not visible, I will have to project it. What about the controller now? I will explain the controller. It is given now. As an input, I will have the position of the boat, the heading of the boat, the direction of the wind, and A and B. And the output will correspond to the angle of my rotor and to the length of the main sheet, and I have only one single state variable in my controller. It will correspond to Q. Q is a Boolean variable, which is either 1 or -1. First, I compute the distance, the algebraic distance to the line. It is given by this formula, where A, B are involved, but also the position of the robot. If I am outside the small corridor, then there is no choice. I will choose the direction Q. So if Q means that I want to go to project on the right or on the left, depending on the wind. So Q will correspond to the sign of E. And since I don't want to change all the time, I want to give some hysteresis to Q in order to avoid the fact that I always change from tag to tag as soon as the sign of E change. So I need some hysteresis. Now I will compute the direction where I want to follow. So this is a nominal direction. Now this direction may be invisible, as it is the case when I satisfy this inequality. So if I satisfy this inequality, I am in the no-go zone. In this case, I will have to project. To project on the right or on the left, so should I go on the left tag or on the right tag? It depends of Q. Okay, so if I am invisible, I take this, but Q will not change, except if I go out from the small corridor. And then I have my low-level controller, my inner loop. So this corresponds to the controller that has been implemented in vaimos. Okay. How can I validate this controller? I can validate by simulation, of course. So I can throw thousands of simulation, different conditions, and in fact I can see that on my simulation, my boat always, for any initial condition, it will follow the line. But it is not a proof. It is not exactly what I want to obtain. I want a mathematical proof of my controller. My boat will stay inside the corridor. That's what I want to do. So I need a theoretical validation, theoretical proof that everything will be okay. And this work has been presented in a paper that has been published 3 years ago. So when the wind is known, the sailboat, which is autonomous because of my controller, is described by a state equation. Recall that I have some uncertainties, so it may be a G-function equation. For this kind of system, how can I prove some stability property? So the idea is to to follow Lyapunov approach. The Lyapunov approach is explained here in a very, very simple way. It is not exactly this, but I try to be simple. If I have a function v, which is always positive, except when x is equal to 0. Okay, so this function v corresponds to some kind of energy. If this function always decreases when x is not equal to 0, then under some conditions that are not given here, if this function always decreases, then we can guess that x will converge to 0. Okay. So what is important here is that I am able to transform a state equation or differential equation into inequalities. Okay. Now what I want to do is something which is quite different. I have a function v which is not always positive. It can be positive or negative. But I will say that the system is v stable if when this function is positive, then it will decrease strictly. Okay, strictly means smaller than epsilon, which is smaller than 0, strictly. Okay, so in this case, I will have some, I will say that the function is v stable, and I will explain what does this mean. I have my state space which is represented here. V is negative inside the gray set. So when it is negative, I don't care what happened inside. But when I am positive, V will decrease. So I will be attracted by this set. The system x dot equal of f of x is V stable if I have this implication. So this proposition should be true. Of course, this for the derivative of v, I know that it is equal. I have an analytical expression since it is the derivative of x at x multiplied by f of x, which corresponds to x dot. Okay, so I know that A implies B. This is equivalent from a logic theory. It is equivalent to B or, so this means or, the negation of A. So A implies B implies either B is true or A is false. What does it mean? So if I apply this to this, I can transform the implication as follows. It means that for all x, because when I have an implication, it means, of course, for all x. So for all x, I have either, so B corresponds to derivative of B with respect to x, multiply, so in x, multiply by f of x negative, or so the negation of this, corresponds to v of x negative. Okay, so this is equivalent to say that if I define it equivalent to say that for all x, so this is negative or this one is negative, it means that the maximum of, so I will take two quantities, will be negative. The first quantity corresponds to v of x, and the first quantity is this one in x multiplied by f of x. If I call this function, for instance, h of x, in fact, I will have the following problem. I have a function, this function. Then I will have a function h like this. It will correspond to h of x. And I will have to prove that it is always positive. And for this can be done by using interval analysis. As explained in the previous part. Okay. So I have proved the theorem, which can be formulated as follows. If this system of inequalities is inconsistent, it means the function h is always negative, then the system is v-stable. And in fact, of course, there is some more efficient method than the one explained here, which consists to use contractor's method in order to be able to solve this problem, to prove that this set of inequalities is inconsistent, even when we have a large number of x. The dimension of x is large. Okay. Now, when I have a differential inclusion, it can be the result can be formulated as follows. The function here excuse me, here f becomes uncertain. So this can be formulated as follows. X dot is equal to f of x. But instead of this now, I have x dot belongs to f of x. So this is equivalent to say that x dot equal to a, where a is unknown, where a belongs to f of x. In practice, I have an analytical expression with respect to f, and this corresponds to an inequality of the form, let's say, phi of a x negative. So it can be expressed as follows. Because if I have something like this, a belongs to a minus a plus, this can be transformed into a smaller than a plus and a greater than a minus. So membership relation as follows. can be transformed into inequalities. So what happened here? I have replaced f of x by a. I have added the fact that a, which corresponds to f of x, belongs to this, which corresponds to inequalities. And I have the same theorem as before, except that now I am able to deal with differential inclusion. So in fact, proving that the differential inclusion is V-stable means amounts to solve that a set of inequalities has no solution, or equivalently, it amounts to prove that a nonlinear function is always positive. And for this, interval analysis can solve the problem. Here, I have an illustration of the differential inclusion. So for each point x, I will have the set of all possible f of x. And in this case, I can have some solution, such as this one, which satisfy the differential inclusion, but we can see that we are not attracted by the corridor, by the set which corresponds to v of x negative. So in this case I have represented here, v of x corresponds to what? The example I have for my boat. I have a corridor. So I will draw now the corridor like this. This is the corridor. And I will try to represent the function I want to deal with. So it will be here. And my function will have this form. It will be positive here, 0 here, negative, and positive. Here, okay, so I represent the function like this. So in my example, if here, for instance, say that I have x2, here I will have, with respect to this direction, the state x1, or x1, or x1 if you want here, not here, excuse me. Here it is v, which depends of x. Here it depends only on of x2. The corridor, the radius of the corridor corresponds to r. For this example, I could have v of x equal of x2 squared minus r2. So it means that when I am here, v of x equals 0, here also v of x equals 0, here v of x equal to minus r2, here x2 equals 0, v of x is negative inside the corridor, and v of x is positive outside the corridor. Positive. So it means that when I am positive, for instance, when I am here, the v will decrease. If I am v stable, v will decrease. So I will go towards the corridor. Once I am inside, if I am v stable, it can happen any kind of thing. We don't know. Okay. So in this example, I am not V-stable because we can see that the differential inclusion is not always attracted to the corridor. So an experimental validation. Once we have made a proof that for the model I am V-stable, does not mean that in practice it will work. The proof has been done for one model, so it is guaranteed for the model, but the model is an approximation of the reality. What is important in robotics is also to have an experimental validation, just to validate the model and all the reasoning. So this corresponds to the collaboration between Einstein and Ifremer. And we can see here a picture of a trajectory that has actually been performed by vaimos. So we can see in red the wanted trajectory. I will try to represent here on the picture. I have here the wanted trajectory. So you have to think like this with respect to 2 points, A and B. A and B. Of course, what happens is the robot will have to stay inside the corridor. So I will represent now the corridor like this. And here I will have the radius R. I have proved that my controller for the algorithm, for the controller I have proposed, I have proved that I am V-stable. And for all kind of wind, so the wind comes from, for instance, this direction. This we don't know, but the controller will adapt itself. So in red, it is the wanted line. Once my controller, my boat has reached, let's say, has gone after B, so as soon as it is inside like this, when it is in the hatch area, then it will switch to another line. For instance, this line, and after it could be this line, and so on. So there is a set of segments that the robot has to follow, but in this presentation, I only deal with one segment. So if the wind comes from this direction, the controller will have to, the boat will follow a line like this, and it could do something like this, and it will be represented green. Okay, that's the kind of trajectory we have. And for the experimental validation, we can see green, that the boat never go out, the vaimos never went out to its corridor. We can see, we can guess that the wind comes from the southwest in this experimentation. So it is experimentation which we call the squared spiral, so with geometric shape, so that we can validate visually that the boat behaves correctly and it has never go out from its corridor. Okay, so now we have made a bigger experiment. One big experiment is Brest-Douarnenez, something like more than 100 kilometers. It was January, about 3 years ago. Okay. So the boat are started from Brest. After when he went out of the Rade de Brest, so maybe a few hours later, maybe five hours later. Here we have met a submarine, a submarine from the army. So we have to take the boat, and of of course, the model is not satisfied anymore. The state equation of the robot is not satisfied, so nothing is anymore guaranteed. But we have to do this. It was we had no choice. After maybe 30 minutes later, we removed the boat. We leave the boat and came back to its line near le Cap de la Chèvre. Cap de la Chèvre is near Douarnenez, and after, in the morning, the vaimos in Douarnenez. The trajectory is represented here. We can see that we do not see where the wind comes from because I have to zoom in to see where the wind comes from. We can see here that because of the boat, we had some we had to move vaimos because of the submarine, and here another problem because of a boat. And on the way back, we stopped here. Okay. Here it's another shape made in the middle of the Atlantic Ocean, made by vaimos. But let me come back to the square spiral. The square spiral corresponds to an actual experiment. On this picture, everything looks perfect, but we can see a small software when we will try to take all data and to zoom in. So I will zoom in here. So it is an experiment. I can move with the trackbar. I can move with respect to time. So if I go, for instance, here, I will zoom. And there I can see that everything is not so perfect. When it is yellow, it means that the boat is in close hold mode. I mean, it is almost not in the go zone, but almost going in the direction of the wind. The arrows here corresponds to the wind that is measured, and we can see here, when it is red, it means that the roll of the boat is too large and the wind sensor is not accurate. In fact, the wind comes from this direction, it is a good wind, but here it measures a wind on the wrong direction. So thanks to the inertial central, we can use this, of course, in order to filter this bad wind direction. When it is yellow, so I have the projection mode, but I zoom out. I stay inside the corridor, and we will see later in the mission. Later in the mission, or for instance here, oops, sorry, here, let's zoom in. We can see that the wind comes from this direction, the heading comes from this direction, so there's still an error between the line and the boat. The vector field makes the boat attracted by the line, but there is still an error. But the error is only a few meters, as indicated here. I have all data. I have the roll, the pitch, the yaw, the distance to the line. So the distance to the line is 0.6 meters, so it's quite small. But if I want to be more accurate, I need to add an integrator, which is not the case here. The speed is something like 2.6 meters per second, which is not so. And here it corresponds to the position of the boat. Here the distance is larger. Oops. For instance, here the distance to the line is 2.49 meters. So we can see that the behavior is quite correct, but not as perfect as indicated in this picture, because when we zoom in, we can see a lot of some imperfection that could be improved. Okay, so now on the last picture, sorry, on the last picture, we can see a trajectory, and I will show a video of vaimos later associated to this mission. It was in the middle of the Atlantic. So the conclusion, which is important, it is when we have proved here that it was possible for a sailboat robot to stay inside the corridor and to accomplish a mission. And we have a proof that it will stay inside the corridor, but via a model. The boat, so this model is an approximation of the behavior of the boat. And this is essential when we will deal with thousands of robots. In this case, if we want to avoid collision, it is important that everybody respects the zone where it has to be. And even if it is guaranteed with respect to the model, the boat will not always satisfy the model. The sensor will not always satisfy the bound they are assumed to satisfy. But what is important is in case of problem, in case of the collision between two robots, we'll be able to say who is the responsible in case of accident, who has to pay in case of accident, which robot is wrong. It is the one who went out of his corridor. And this kind of set membership approach for control is essential because in order to copy what happened for traffic jam, when we have thousands of cars, everybody has to stay inside the right corridor. There is some red line we have where we have to stop. When it's green, we have to go. We have rules for this. And we think that when we have thousands of robots, this kind of set membership constraints is essential to make a complex system working. To finish, I will show so this mission in the middle of the Atlantic Ocean. I will show a video which at the beginning and at the end of the mission. Here is the Thalassa boat of Ifremer. Vaimos, it is in the middle of the Atlantic Ocean. And here is Vaimos. Here, Olivier Ménage, one of the responsible of the project. The Zodiac, they take the boat far to the Thalassa in order to avoid any collision. Vaimos is starting its calibration in order to go to take some measurements for several days. And several days later, it will come back. Several days later, it comes back. And it has performed this trajectory. When we zoom in, we could see some zigzags. The triangle, so at the end of the mission, the Thalassa has had to catch back the Vaimos. So to wait the Thalassa, Vaimos had to do several times the triangle. And after the captain of the Thalassa changed his mind, and he had to do some squares inside of area in order to catch, to fetch the robot. This trajectory corresponds to 350 kilometers.